Yeah, so I will, okay, so I'll put that bit later, okay, so I can't copy paste from this, I'll do that, yeah, after the lecture. So, yeah, so this is going to be the place where all course materials will be there. I've already put some of the reference materials that we are going to use for this course, and all lectures, slides, if at all I write notes, they will all be there. Okay. Yeah, we'll also have a course web page here, but these days I prefer putting everything in the Google form or a Google Drive. So I'll just maybe I'll copy paste the Drive link, which is more useful. Okay, so let's see. So this is a link for Google Drive. Okay, so you can just access it right away. I'll give the form also in a second. It's a Google form. Okay. So I'll also be occasionally updating this course web page, but I prefer doing it through this Google Drive. So I've created a Google Doc there. So all the lecture details, I'll just put it there. Okay, so that it's easy for you as well as for me. Okay, so yeah. So for each lecture, lecture-wise content and reference materials, links, if any, will be there. Okay. Okay. So yeah, so this offering of the course is going to be, see, this is a topics course, so usually there is no fixed syllabus. You might have seen over the years there has been different contents. There was at some point of time graph algorithms, some point of time approximation algorithms, parameterized algorithms, and so on. So this time I'm going to focus on the analysis part, not just design. Okay, in fact, no design at all. It will be focused on analysis. Okay. So in particular, our primary objective will be to explore paradigms that go beyond worst case analysis of algorithms. Okay. In particular, we'll be focusing on smooth analysis and probabilistic analysis of algorithms. We'll be seeing what they are exactly. Yeah, so our primary objective is to develop techniques for such an analysis. But more than techniques, we will be seeing specific algorithms and their analysis. Particularly, the focus will be on simple algorithms, which are used in practice, but the performance is not explained mathematically or was not explained mathematically using the existing paradigms. Okay. Yeah, so this is, I just copy pasted the content. I'll just go through. So this course essentially requires a good feel for probability, though you don't need much of probability theory and so on. We need just basic understanding of distributions and so on. So we'll set it up along the way. So, okay, so whatever is needed, I'll be covering. I'll be touching upon or doing it in fair amount of detail. So the primary content is going to be smooth analysis as well as probabilistic analysis. So here we'll try to demonstrate smooth analysis to specific algorithms. Okay. But like I said, in particular, interesting are those which are simple to implement or practically efficient algorithms. We'll be looking at algorithms for knapsack problems, integer programming, traveling salesman problem. In fact, traveling salesman problem, we'll see several algorithms. And then we'll also look at the clustering problem, the k-means clustering algorithm for the same. And so towards the end, we'll also, so this will roughly be 6 to 7 weeks. Probability, it will be roughly 1 to 2 weeks, but I won't be doing it often. So next lecture I'll do a bit of probability. After that, whenever we need a new concept, we'll introduce it. Okay. Yeah, so towards the end, we'll be looking at the probabilistic analysis of algorithms. Yeah, so the only point is these two are kind of, so chronologically probabilistic analysis is the one which came first, and smooth analysis, you can actually say that it's a specific variant of probabilistic analysis. Yeah, so I'm preferring to do smooth analysis first because there is no dependence on probabilistic analysis first up. I mean, that is one thing. And second thing is the crucial part of project will be basically focused on smooth analysis, which is more state of art. So probabilistic analysis I still want to do because there are some interesting techniques which could be useful. Okay, so particularly the concentration bounds or ways of developing concentration bounds for Euclidean optimization problems. Okay, yeah. So for the smooth analysis, there is no textbook as of it. It's a relatively new paradigm. So I'll be referring to two lecture notes, one by Bodo Monte and one by Heiko Rögling. Okay, so this is called Beyond Worst Case Analysis of Algorithms. This is called Probabilistic Analysis of Algorithms. But in both, I mean, primary objective is basically smooth analysis. For the probabilistic analysis, there are two textbooks which we will be referring to, at least part of it. So yeah. So like I said, I mean, since reference materials are not standard, I'm going to put as much as and when I have access to, I mean, I'm going to put all the reference materials in that Google folder. Okay, so that Google Drive folder, so that you will not struggle to find references. Okay, so let's come to the most important part. Evaluated assignment, I mean, evaluation scheme. Okay, so yeah, yeah. So there will be evaluated assignments. Together, they will contribute 20%. Okay. So that each assignment will be 10%. There will be two assignments. As usually the practice, I will always give one extra assignment. Okay. In all elective courses, I tend to give one extra assignment so that the best 2 of 3 will be considered. Okay. So there will be a mid-sem and there will be an end-sem. So this together, the exam and the written components, this will contribute 50%. Okay. So all these will be in take-home format. Okay. So evaluated assignments and mid-sem, end-sem will be take-home format. Will be conducted through Moodle. Okay. So I will come to the specific very soon. The project component will be contributing 50%. So 50, 50, 100. Okay. So now we'll go into the details. So evaluated assignments, basically take home exams, okay, like a take home exam, but only thing is it will be 15 days. You'll have 15 days time. Yeah, so these are the rules. You'll have to solve individually and so on. Okay. Yeah, one thing to keep in mind is in this course, this is very important. Okay. See, all we need is, so all we'll look into is how well are you able to apply the ideas, or how well are you able to come up with new ideas in solving a problem. Okay. So the suggestion is not to discuss with each other, but try to come up with your own solution. Okay, even if it is incorrect, it's fine. Okay, so yeah, in fact, the grading policy is going to be, if you come up with a really good idea, there's a possibility that you will get full credit for that. Okay, yeah, even if it does not solve the given problem, even if it is not close to solving the problem, but if it is completely out of the box, we'll respect that. Okay, so keep this in mind, okay, while attempting the assignments. So this is like 15 days, I believe it should be enough. So you can expect 4 to 5 questions. Okay. So the exams again through Moodle, but only thing is we'll have a window of 48 hours this can be negotiated. I mean, we can discuss, but not much. But what I'm insisting is I want to have this condition. Once you start an attempt, I mean, you'll be allowed to do only one attempt. Once you start an attempt, you have to submit the solution within 3 hours. So there will be a window of 48 hours, but you have to complete within 3 hours. Okay. So, I mean, the questions will be set in such a way that you should be able to solve it in 2 hours and 1 hour for whatever, writing down the solution and so on. Yeah. So these are the standard rules and so on. So, yeah. So any questions about assignments and exams? So one thing, assignments will be purely mathematical. So this course is going to be purely mathematical in nature. Okay. So there will not be any programming assignments or anything of that sort or empirical stuff. Okay. So it will be completely mathematical, like all theory courses are. Okay. So the assignments means basically you'll be given some problems, you have to write the solution. Similarly, exams you'll have to answer, you don't have to write a program or whatever. Okay, so yeah. So these are the tentative dates. Assignment 1, yeah, maybe we'll start next week. So this is February 2nd, right? Yeah, in a week's time. So 15 days will be there. Assignment 2 will be in March. Assignment 3 will decide on the date. Could be April, I think. So mid-sem, I'm proposing it as March 12 to 14. End-sem, April 32. So end-sem again, so there is an end-sem schedule given in the academic calendar. So since we are going to have it in the take-home mode, I would say it's better to get it done early, okay, a week before the regular end-sems. So that during that time we could do project evaluations, okay. So otherwise, it's going to be a trouble, I think, with this take-home format end-sem overlapping with other end-sems. Okay. Yeah. So I request all of you to mark these dates and not to agree for any other evaluations or any other activity during that. Yeah. I'll take a couple of questions, if any, on these. Hello. Can somebody confirm if I'm audible?
Yeah, Professor, you're audible.
Yes, sir.
Yeah, thank you. Okay. Okay.
What about the project? Okay.
Yeah, we'll talk about that. Yes. Project. Yeah. That's going to be next slide. Okay, so here comes the most important part. Okay, yeah. So this project, the format of the project, I'm not completely decided yet. Okay, so I'll just discuss it now. So usually for theory courses, the default format is to do a detailed reading of a research article or a couple of research articles, and yeah, so there will be multiple meetings, interactions which will be evaluated, and then followed by a final presentation or a viva or a viva. Okay. So I mean, these are designed in such a way that when people have time or highly motivated, one can also pursue a related research question in that. Okay, it depends on individual's taste, load, whatever. Okay. So, but so given this course, I mean, I haven't yet discussed the full context of the course, but the context of the course is such a way that even though the course is mathematical, so the origin of this topic was motivated by practical relevance. Yeah. So it's mainly because the traditional worst case analysis, which is what we are taught in most of the regular algorithms course. Okay. So the performance guarantee is going to be worst case. That is, on every input, the guarantee has to be met. Okay. But however, it is observed that such performance guarantees are not sufficient for particularly industry level applications or scientific applications. Okay, where we have real world data and work with real world data. So I'm thinking about also having hybrid projects where major part will be implementing and doing a performance evaluation of an algorithm, and then looking at a theoretical explanation of the same. Okay, so this is something I have never done as a course project. Okay, so what I want to do is I'll just take a survey. Okay, so here is Google form. Yeah, I'll copy paste in the chat window. Okay, so please fill the Google form by February 4th evening. So to give your feedback or give your opinion, I'll post a couple of questions there regarding the project, so that we can make a decision of. So I'll see how many of you are interested in such a thing, and so I'll also get time to think about it. Is it feasible and so on. Okay, so I'll put link here. So this is the Google form. I request all of you to fill. Okay, so it's anonymized, so your names will not be collected. Okay, so yeah. So the rest of the details about the project I'll post soon after this deadline. Okay, so I'll just take a decision. If it is hybrid, then we'll have to come up with a way of evaluating this and so on. Okay, like I said, I haven't done this before, but I feel this could be appropriate because this course, the origin basically comes from applications or experimental necessities. Okay, so yeah. Yeah, so this is again, there will be 4 lectures per week initially. Okay, so that is, it's because it's a 12 credit course. Okay, only thing is after the project commences, we'll reassess and we'll probably reduce it to 3 lectures per week. Okay, so depending on, because project is contributing 50%, I believe more time should be given for project. So I'll reduce the number of lectures. Okay, so yeah. We'll also have tutorials based on if there are problem sets to be discussed and so on. So, yeah, any questions, suggestions?
Professor, one doubt. Like
Yes,
project is going to be
yes.
like NSEM, like it will be evaluated at the end, either by the Viva or by the theoretical explanation followed by the algorithm, or it will be like
So see, there will be a presentation, okay, public presentation, that is presentation to the class, and I'm also thinking of having a short viva. Okay, so see, in the website I have already mentioned some division of marks, but like I said, I mean, depending on the format, we'll see. Okay, so this division of marks will be so see. At least my idea is for, suppose it's a theoretical project, so then it will be, so there will be one first interim meeting. Okay, so where you do a preliminary reading of the paper, or I mean articles, whatever source, and then so we have a discussion. Okay, so that will have some small percentage, and then followed by a full-fledged meeting, again one-on-one. So you'll meet me and explain the content completely as much as you understand, then followed by a presentation, oral presentation based on slide, I mean along with slides, which is given to the whole class. Okay, so this is how I used to usually conduct the projects. So this time I'm also adding a final component, that is a viva. Okay, a short viva in the end. That is after the presentation, there will be a 10 to 15 minutes viva. Okay, just to see how much you understood or whatever. So the division of marks among them, I'll announce. So yeah, in the course page, I have done some division, but it's not final yet. Okay, so after seeing the feedback, I'll take a decision. Okay, so yeah, so in what I have written in the web page, it's like so first meeting will be 5%, the review meeting will be 10%, viva will be 10%, and presentation will be 15%, and short report will be 5%. Okay, so I've also I'm just reading it out. So this is also about criticizing another report, that is 5%. Okay, so that is just a thought process I had. Like I said, I'll take the survey and I look into the survey and then take a decision. Okay.
Sir, I have a question.
Yes.
So, in the default form of the project, you said that the project is going to be dependent on a research article. Uh,
Yes. Yeah.
in the hybrid project, so the algorithm that we will be implementing, will that also be based on a research article, or
It
we?
will be research article. I mean, in the sense that say usually this engineering articles, right? I mean, they will be doing experimental evaluation, so it will be on a research article. But usually, this algorithms, at least my personal interest is to have algorithms which are simple to implement. Okay, so those kind of. So I'm not so keen to implement algorithms which are very complicated to understand because I don't feel they are practically useful as such. Okay, so algorithm should be easily understandable. So it could be a traditional algorithm or an I mean textbook algorithm, or it could be an algorithm from a research article.
Okay. So it'll be like verifying the performance.
Yeah, performance, but the performance evaluation, the way we do it will be different,
Okay.
different from what has been done in the literature or whatever. Yeah.
Thank you.
Yes, Sanket, yes. List of research articles I will be proposing. Okay, so once I finalize the format, I already have a short list of articles. Uh, we'll have a selection process. Okay, first come, first serve allocation or whatever. I'll be sharing the list and so on. Yeah. Okay, good. So did I share the link for the form? Yeah, I've shared, right? So please fill the form as soon as possible so that we can make a decision. Okay, so I just want to know your interest and so on. If there is significant interest for this hybrid kind of project, we'll also do that. Okay, so yeah. Okay. Yeah, so this is I mean, whatever the disco notice. Okay, this should be there in any first lecture. Okay, good. So the rest 20 minutes, I am going to give a context for need for looking beyond worst case analysis. And I'll also talk about different algorithm analysis paradigms along with worst case. And yeah, if possible, I'll give an introduction to smooth analysis as well. Okay. So please tell me if what I write is visible to everyone.
Yes, sir.
Okay, good. So let's say A is an algorithm. Okay. And I'm looking at some performance measure. It could be time complexity, it could be any other quality of the output or whatever. Okay. So TAB, some performance measure. Or let's say T. I won't even need T. Okay. I just say T, T with respect to some input. Okay. Measure of T. Okay. So example, time complexity. So we'll also be looking at the quality of the output later on. Okay. So some might wonder, okay, what is there about quality of output and so on. So we will also be looking at, you might have heard of about algorithms which won't compute exact solution. They will be called approximation algorithms. They will give solutions which are close enough. So that is when the quality of output becomes important. Okay, so it could be anything. So this could be some measure. Okay, so we'll imagine the measure being high is bad, measure being small is good. Let's imagine that way. Okay, so now what is the worst case complexity or worst case performance of A? Worst A, that is the worst case performance of A. So how will you define? So you run over all inputs x, set of all inputs, so T of x. So if you want to see this as a measure in terms of the input length, then you can run over, so you can take it as run over all inputs of length n. Okay. So for example, if when we say that merge sort requires order of n log n time, or quick sort requires order of n square time, so we basically mean the worst case analysis. That is, on all inputs, the algorithm is guaranteed to run in so much time. Okay. So this is the traditional performance measure. In all of our algorithms courses, or for long algorithm analysis and algorithm designers, they basically focused on these. Okay. So I mean, see, this is a good guarantee. Okay, so once you have this guarantee, this is something you can completely trust, irrespective of the input. So when I say worst case performance is bounded by t, or so bounded by, say, some function, say f of n, that means no matter what the input is, the performance is bounded by that. Okay. So it is good. I mean, it's in fact, once you have such an algorithm, it's always good. One can use it anywhere with the given promise. Okay. So, however, there are scenarios where, so the real world scenario and this worst case scenario, they differ. Okay. So I'll give you some examples. Okay. So a couple of examples. Example 1. So let's look at the problem of the traveling salesman problem. So input n cities. Let's say so P1, etc., Pn. Okay. So output, so with distances between every pair of cities. Okay. Now output, a tour, that is a cycle, P1, P2, etc., Pn, P1, such that summation, okay, sorry, this I should have different indices, I1, I2, In, comma I1, such a way that summation j equal to 1 to n, distance Pij, Pij plus 1, whatever, modulo n plus 1 is minimum. Okay. Or in other words, pictorially, so you have n cities with some distances given. Okay, so city 1, city 2, and so on. We can visualize it as a graph. Now what we want is a Hamiltonian cycle such that, so what are the edge weights? So graph is a complete graph where the edge weights are the distance between cities. So here the edge weight is distance between 1, 2. So we want a Hamiltonian cycle, that is a cycle which visits every vertex exactly once, or in other words, a cycle on n vertices. Okay, such a way that the edge weight of the cycle is minimum. So for example, this is one such. Well, this may not be exactly, but yeah, it's pretty much. Okay, so this is called a TSP tour, or traveling salesman or salesperson's tour. Okay, so he wants to travel every city exactly once and come back to the original destination, original source city. Okay. So this problem, how many of you haven't heard of this problem? Okay, so yeah, there's one person haven't heard. Have you heard of Hamiltonian cycle before? Okay, so this problem, see, this problem occurs, it doesn't matter even if you haven't heard of. Okay, so this occurs very often. So for example, all these logistic guys, right? So there's logistic persons. So for example, Amazon delivery or Flipkart delivery or any other courier delivery person. So there will be a depot. Okay, so this will be one depot that he's starting from. So you'll have to deliver articles at some, say, 10 or 20 or some n number of locations. Okay, yeah, so he has a bike or some vehicle, and then so what he has to do is he has to have an optimal tour, right? Assuming that longer distance, the larger is the money spent. So basically he wants to visit every place exactly once and then come back to the depot or come back to the office. Okay, so that's why it's called a traveling salesman. Okay, so now in the current context, it's in fact a travel courier delivery person or postal delivery person or postman. This problem. Okay, yeah, so those who have seen, you might have also seen some algorithms, right? Some of you would have seen a dynamic programming algorithm, if at all you have seen it. Anyway, does not matter. Okay, so the point I wanted to mention is this problem has been studied, in fact has been studied even before proper computers existed. Okay, so this problem has been studied since the 50s or even before. So this is a genuine problem, right? Even when industrialization happened, it's very natural to have this kind of situation. A person will have to drop, yeah, courier or postal items or any other material at certain places and come back to the original. So in the process, I mean, he or she would like to optimize the distance traveled or the cost or whatever. Okay. Yeah. So the interesting fact here is like this problem has numerous algorithms. Okay, what we call as heuristic algorithms. If you look at the literature since 1950s, people have not even 1950s, in fact 1940s, 30s itself, people have studied this problem. So one thing that I would like to mention is from a complexity viewpoint, this problem is termed as NP hard. So TSP is NP hard. What does it really mean? So in layman terms, it basically means you cannot expect polynomial time algorithm. What do I mean by polynomial time algorithm? So when there are n cities, I want an algorithm which runs in n to the power some constant. That is a polynomial in n. The number of operations performed by the algorithms. So what are the operations? I mean, any operation, so arithmetic operation or comparison operation, any of that will count as one operation. Okay, so I mean each of them will count as one operation. So if you have n cities, ideally I would like to have order n operation, that is a constant times n, 100n or 50n or whatever, or n square, n cube, or n to the 5. So n to the any constant is a polynomial. Okay, so that is traditionally considered as efficient. Okay, so TSP is NP hard. It basically means you cannot have such an algorithm unless something happens. Okay, let's not really say something what that something happens. That something significant happens in theory of computation. Okay, so there is a conjecture in theory of computation that certain problems, certain set of problems are unlikely to admit polynomial time algorithms. Okay, so TSP is one among them. In fact, this is a very celebrated problem. In fact, there is a institute called Clay Math Institute, which they announced this among 6 others as the 7 millennial problems for mathematics. If you solve them, they'll give you an award of some $1 million or whatever. Nevertheless, never mind all that. Okay. So in other words, obtaining efficient algorithm for this problem is hard. That is the message that we take. Okay. So we are not going to prove that it is hard to get an algorithm and so on. But then what would the real world people do, right? Okay, if you are having an exponential time algorithm, what do I mean by exponential time? Say 2 power n algorithm. Okay, so if you are having a 2 power n algorithm, the moment say n is 20, so any algorithm will take say 2 power 20, right? 2 power 20 is already huge. So if I make it 30, then this becomes even huger. The moment it hits 100, then it's really impossible. 2 power 100. We'll have to run the algorithm even in a fastest computer for our lifetime. So that's why exponential values for runtime are considered to be bad. Okay, so that way, so TSP being NP hard basically means that okay, practical people have no hope really. Okay, but is it that they don't really solve this problem? They do, right? So if you see this delivery, I mean currently, I mean more modern times, the e-commerce companies or earlier logistic companies, they do have algorithms. They have systems which produce solutions. Okay, so drivers usually get their route. Even Google Maps, right? It also does some route calculation. Okay, so well, it may not optimize that much. I mean, it has some other functionalities and so on, and parameters or constraints and so on. But whatever, but practically it is done. Okay, so but what are those algorithms? So there are several algorithms which do that. Okay, so there are two kinds of algorithms. So one is people settle for exponential time. Another is people say, okay, maybe finding the best possible is difficult. Maybe what I'll compromise. I'll go something small. I mean, costlier but easier to compute. Okay, so that is when this approximation algorithms came into picture. Okay, so if obtaining exact solution is hard, when I say hard, it's time consuming. Okay, computers will take days or months or years to compute. People settle for close enough approximations. Okay, so yeah, so this is how approximation algorithms originated. Okay, so there is in fact a course on this approximation algorithms, which is being currently offered. So now for TSP, that is what people did. People came up with heuristics, what are called as heuristics. The reason that we call it as heuristics because it's not kind of, see, when we say algorithm, right? Algorithm is something whose correctness and performance guarantees are proven. Heuristic is something which does well in most of the cases, but it may not do well in several cases too. Okay, so that's the reason why in literature you'll see heuristics, the term heuristics. Okay, it originally came from this AI community where most of the algorithms there are called heuristics. Okay, so yeah, so people settle for heuristics or approximation algorithms for TSP, and there are several of them. Okay, so one such algorithm is called the 2-opt algorithm. It's just a simple algorithm, so I'll just demonstrate it pictorially. So this is an instance of TSP. Okay. Yeah, so the way I have drawn it, it might be the optimal TSP as well. Nevertheless, let's not worry about that. So the algorithm, what it does is the following. Okay, it starts with some tour. Okay, so begin with some tour. Let tau be some tour. Okay, so for example, this tour I have drawn here. Every time, every iteration, the algorithm basically looks for two edges, pair of edges. Okay, so now the pair of edges is 1, 2, and 3, 4. So Notice that what I have drawn here is also a tour, right? It's a valid Hamiltonian cycle. It may not be the optimal. Okay, so some arbitrary tour. You can just pretend that the tour you begin with is 1 to n. That is it. The city is numbered 1 to n. That is the order. So go from 1 to 2, 2 to 3, etc., then 1 n to 1. Okay. Now what the algorithm does is, so let's look at this. Now let's look at the possibility of swapping this. What do I mean? So now see, going from 1 to 2 and then so on, then 3 to 4. Okay. I mean, I'm assuming that they need not be neighbors or whatever. I just chosen the edges arbitrarily here. Okay. So these edges are chosen arbitrarily. So can you tell me, can we remove these edges and do some add again 2 edges to get a different tour? What are the possibilities? So what if I go, so from 2, go to 2, go to 4, okay, then 5, 6, 7, 8, 9, 1, then again I go to 3. Is this a valid tour? So I remove these edges. This is a valid tour, right? So what is a new tour? 1, 3, 2, 4, 5, 6, 7, 8, 9. Right? This is the only possibility. The other you can also do the other swap, but it won't give it 2. It will give 2 tours, okay, of a subset of vertices. Now, what this algorithm does is it just checks if this is a shorter tour or not. Okay, so I'll write it here. So for every pair EF of edges in T, see if the new tour obtained by swapping the endpoints. I'm not really writing it precisely here, okay? So it's a bit painful to write it exactly, but I hope this picture makes it clear, right? What do I mean by swapping endpoints? E and F has smaller cost. If S update tau to that tour and go further. So every time you just continue, okay? So until no further improvement is possible. So repeat this. Above until no further improvement is possible. Is the algorithm clear to everyone? It's a fairly simple algorithm. Okay, you start with some ordering of the cities, okay, which is basically one Hamiltonian cycle. For every pair of edges, you keep on doing it. Okay, see, after doing this, I might end up considering this edge with something else and so on. The pairs keep on changing, the tour keeps on changing, and so on. The condition that we want is the overall weight or the cost of the tour, that is sum of the edges taken in the tour, should go down. Okay, if it decreases, so if this cost is smaller than the original tour, I'll take that. The moment no further improvement is possible, we'll stop. Okay. Yeah, it's a very natural algorithm, right? You start with some solution and then keep on improving it as much as long as it is possible. The moment it is not possible, you stop it. Yeah, so now this red colored edges are removed, replaced with green colored. If at all the tour cost is smaller, then you consider another pair and keep on doing it. Okay, so this is called two-opt algorithm. There is a general version of it called k-opt algorithm, where you will consider k edges instead of two edges. So the two coming from the fact that you are doing this exchange with the two edges. Okay, so the two edges. K-opt is something, say k is 3, then you will have 3 edges. Then again, I mean, then this computation, there could be multiple tours, okay, if you have 3 edges. So when there are 2 edges, there is only another new tour, okay. Yeah, so in general, this is called Kernighan's k-opt algorithm. So the Kernighan, right? Kernighan, Ritchie, Kernighan. So the same person invented this algorithm. Two-opt, I think, was known much before, but whatever. So if you look at the description of the algorithm, it's pretty simple, right? Anybody who learned C programming or any other programming language can implement this algorithm. Is that not? You don't really need anything more, right? You in fact you need to know arrays, how to store ordering of the vertices, and then how to compute the distance. So if somebody gives you a procedure to compute the distances, that's it, done, right? So given that the problem is NP hard, so what certainly we can say about this algorithm? Yeah, I'll listen to a couple of you and then wind up the lecture for today. So okay, Sarthak, you said something. Sorry, I didn't see. What was it? 1-3. Okay, sorry, I didn't see the chat at all. Okay. Okay, good. So there were suggestions. Okay, so 1, 3, 2, 4. Yeah, good. Okay, so so based on the fact that TSP is NP hard, that is, you cannot have a polynomial time algorithm, unless something drastic happens. So what can you say for sure about this algorithm? Yeah, this is not optimal. One is either the output is not optimal, or yeah, k. So either the number of times you will have to do this updation. So let's call this as a two-opt step. This exchange, right? Obtaining a new tour by this exchange. Let's call it as a two-opt step. So either the number of two-opt steps will be exponential, or the solution will not be optimal. One of them will be guaranteed, right? Both cannot occur. Okay. Yeah, so either exponential number of iterations or solution not optimal. Yeah, but the funny fact about this algorithm is, so this has been used for ages, okay? So this is practically fantastic algorithm. Most of the industry people, they like this algorithm. They use it very well, very, very widely used. And even experimental people, they have run this algorithm on lots of test data, sample data, or benchmark data, and saw that the performance is excellent. Okay. But till 2000, I think 2008 or maybe 2010, there was no mathematical explanation of this. Why it works? See, it's clear, okay, because it's NP hard, one of that can happen. I mean, so both cannot be good. That is, either running time should be bad or performance should be bad. That is, the tour will not be the minimum. Okay, that everybody knew. Yeah, till the late 90s and 2000s, people didn't have a proper explanation for why practically it is working. So it was in 1999, some set of people came up with worst case examples. They proved that there are example instances where you can prove that the number of iterations is exponential. That is 2 power n or something like that, 2 power n by 10 or whatever. Okay. But still nobody had what is a guarantee. So there was some guarantee which said, okay, so in the worst case, this algorithm will give a performance ratio of order of log n. That is, if you take the optimal tour and the tour output by this algorithm, So true output by this algorithm will be log n factor, that is log n times optimal value. Okay, so there were such guarantees, but still it didn't explain why practically people are using it. Okay, so this is where, so the worst case analysis, okay, it said that the algorithm is bad. That is what something we already knew, because TSP is NP hard means it has to be bad. That's no question about it, right? Because if this was good, then something would happen in complexity theory. That is P equal to NP would happen. That is something a huge set of people believed. It is not true. Also, people believe that it's very hard to prove or disprove it. Okay. So, assuming those people, or assuming that we believe in those people, we know that the algorithm is going to be bad. Okay. But then why it is being used by industry people? That is completely, that's, I mean, in a way, it is a failure of this theory field, right? Algorithm field. See, what is the purpose of theory? We should develop theory which also helps practical people, right? So, of course, I just taught ADSA course where I would just say, no, we'll do worst case analysis, forget about it's practical or whatever. Okay, that's when we teach a first course, that is how we do, because if you, the moment you say multiple paradigms, people will get confused. Okay, so you need to teach them worst case analysis, that's all you say. But the moment you become mature, this is what you are going to say. No, this has problems. Okay, so the origin of beyond worst case basically from such scenarios. This is not just one example, there are thousands of such examples. If you go to machine learning literature or AI literature or systems literature, there will be thousands of such algorithms which people use. Okay, but if you go and ask a theoretician, no, this is an NP hard problem, you cannot solve efficiently. But people will be, there is SAT solver, celebrated SAT solvers, okay, which practically people use. Satisfiability solvers, okay, but satisfiability is again a notorious NP hard problem. So yeah, so our first example is going to be, we can develop a template for analysis of this, okay, called smooth analysis, where we can explain why this algorithm performs really well in practice. Okay, yeah, so I think I should stop, it's already 6 o'clock. So yeah, so we'll set up the notions for smooth analysis. What do you mean by smooth complexity or smooth analysis of an algorithm? Okay, how it differs from the more popular average case algorithm, or I'll also tell you why average case analysis fails in most of the cases. It does not explain practical behavior of the algorithm. Okay, so like I said, we will take a purely mathematical approach, but our idea will be, so like I said, we'll be taking such simple algorithms. See, the point is, industry people, I mean, some of you must have been in the industry already, usually like simple algorithms, okay? Anybody, in fact. See, the algorithm is simple, it's easy to implement, that's good, right? Because if something goes wrong, it's easy to locate. If you have some 10,000s of codes for such some algorithm, say some graph algorithm, it's almost impossible to rectify if something goes wrong, or improvise if you want to improve. Okay, so it's always nice to have simple algorithms. So at least what we will focus is, we look at simple algorithms and try to explain their behavior, why they are practically good, or why certain kinds of algorithms will not be practically good. Okay, so that's going to be our main purpose. So in the course page, I have also mentioned Tim Roughgarden's page. So he also taught a very similar course, but I'm afraid that I will not be covering majority of his course material, because I think his focus has been more on this kind of algorithms for systems, okay, yeah, particularly memory optimization and so on. So I would rather look into optimization problems and the standard optimization problems. If time permits, I'll also take a couple of examples from Tim Roughgarden's lectures. Okay. Okay, so I should stop now. Thank you all. So tomorrow's lecture will be at 11, I think. Yeah, 11. Okay, so see you all tomorrow. So please don't forget to fill the form. Okay. Thank you.
Thank you, sir.
Yeah, thank you. Bye.
Thank you, sir.
Thank you, sir.
Bye. Thank you.
Sir,
Yes. Yeah.